Alright, so in that last video I had marked over here some of these values, but I am just going to emphasize by writing them under each of these curves. So again, these sample proportions, so again, this is a p-hat axis now on the horizontal axis for these graphs. And so for this particular curve, mu p-hat was approximated by the value 0.5968. And sigma p-hat was approximated by the value 0.1545. So these values that we saw given on the table on the right. Okay. When n was 50, so in this case n was 10, so here when n was 50, now mu p-hat was approximated with the value 0.6002, and sigma p-hat was approximated with the value 0.069. And in our final simulation, where n was 100, mu p-hat was approximated by the value 0.6001, and sigma p-hat was approximated by the value 0.0497. Alright, so now this next page here. So in looking at comparing those three graphs on the previous page, we should notice the following. So first off, the shape of the resulting histogram of those sample proportions looks more and more like that of a normal curve as n gets larger. Okay, so again, all of them kind of had a curve to them, but again, that first graph had lots of gaps in it that were filled as we were making n larger and larger. The population proportion is 0.6. Okay, that's what we filled in for p, so p was 0.6. And the mean of each of these sampling distributions was very close to 0.6. Okay, so something that we noticed in the previous section, the mean of our original population, mu sub x, was very close to mu sub x bar on all of those, no matter what the sample size was. But just like in the last section, the population standard deviations were affected by the sample size. So the population standard deviation for the sampling distribution, here we saw gets smaller as n gets larger, okay, which makes those curves more concentrated near that central value of 0.6. All right, so these results are formalized below. Okay, so for qualitative data. So if you take a random sample of size little n from a population with a population proportion p, this distribution of p-hat has a mean. Mu of that p-hat distribution is just equal to p. So we saw that. The mean of each of those distributions was very close to 0.6. And now the standard deviation formula here is a bit more complicated. So here we're going to take the square root of p times 1 minus p divided by n. So we need to be careful when we type this on the calculator that it's taking the square root of this entire quantity. So now the standard deviation of the random variable p-hat gets smaller as n gets larger, since as n gets larger the values of p-hat were less spread out. Alright, so that gives us the second most amazing, or kind of tied for first maybe in the last section, not that qualitative data is less interesting than quantitative, but our second really amazing theorem in statistics, which is the central limit theorem for proportions. So if a sample size of little n is taken from a population with a proportion p, then this distribution of p-hat is approximately normal if the following conditions are met. Okay, so the first thing we need is we need n times p to be at least 10, and we need n times 1 minus p to be at least 10. Okay, that is a very different rule than the sample size in the previous section for quantitative data. For quantitative data, oftentimes n of 30 is large enough, but for qualitative data we need more data to make these two inequalities true. And the second condition that sometimes we can't check because we don't have the population size, but Again, for the binomial distribution, we need independent events that, the categorization of one object doesn't affect the categorization of another. So we would need cap n, our population size, to be greater than or equal to 20 times little n. Now, many times the population size is not given or it's not even known. In these cases, we assume that cap n is large enough to make cap n at least 20 times little n be a true statement. So oftentimes you're really just checking this first condition, which is a sample size check, basically like we had for quantitative data, but we're not checking that, just n is at least 30. It also depends on the value of p. All right, so now that you know when the distribution of the sample proportion will look like a normal distribution, once again we can find probabilities related to the sample proportion. So remember, the mean of the sampling distribution of the proportion is just the population percentage. So mu p hat is simply just the value of p. Again, those two symbols, mu sub p hat and p, stand for different things, but their values are exactly the same. But the standard deviation of the sampling distribution of the proportion, sigma p hat, is actually more complicated to compute. And so this one we do need to just be a bit careful that we are taking the square root of this entire quantity, p times 1 minus p divided by n. Okay. So the steps for using StatCrunch and the TI-84 to compute probabilities and values of the random variable for normal distributions are the same as they were earlier in the chapter, except now the mean will be the value of p, and the standard deviation is this complicated square root p1 minus p over n. So that means if we're using the TI-84 calculator, when we're looking at normal CDF, again we're going to have lower, upper, and then the next input is the mean, which for this will be p, and then the last input is the standard deviation, which right in this input we're going to type in that square root symbol and that quantity p1 minus p divided by n. And similarly for inverse norm, that first input is still going to be area to the left. The next input is for the mean, which in this case is p, and the last input is the standard deviation, which again is this complicated formula with the square root p1 minus p over n. And again, which one we use depends on what we're being asked to find. If we want a probability, we use normal CDF. If we want a value of the random variable, we use inverse norm.